Chapter 2, Sections 6 and 7 for precalc. We're going to look at rational functions. So we're looking at this example first. We should be able to graph it. And to graph any kind of equation, we should just know we can make a table for that. So we plug negative 5 in there. We're going to do like negative 5 times 2 is negative 10. Negative 10 plus 1 would be negative 9. And then negative 5 plus 1 will be over negative 4. So you have 9/4, which is 2 1/4. So we can go through this table and find all the values for y, for those x values. We can also use a graphing calculator. To do that. And when you're doing that for the rational function, make sure you use your parentheses. So it's the quantity of 2x plus 1 divided by the quantity of x plus 1. Make sure you use quantity for the. And so if we actually plug that in the calculator, and then we can look at the table feature for a calculator, and we can find. And so we can then plot these points in the graph. So something funny kind of happens on the graph right here. And if you recall your rational functions from Algebra 2, you'll see how it's increasing here. It keeps increasing infinitely upwards. And then this also, these points are decreasing infinitely downwards, and then it actually curves to the right and flattens out. And so remembering from Algebra 2, we should recall, or hope to recall, that at this value there is an asymptote, which is a line that the graph is approaching but never touching. And there happens to be one right here as well. And you can see how the graph kind of flattens out. Another way of stating this is as we approach the x value of negative 1, our y values go down and up forever, so positive, negative, infinity. We can also state that as the y values get closer and closer to 2, the x values go right forever and left forever, so like positive, negative, infinity. So we'll have the definition again here in a second. And so when you deal with fractions like this, we've already stated in previous sections in this class how we got to watch our denominator. We should state here that x cannot equal negative 1 because that's our domain. We can't have a denominator 0. And that kind of correlates here to our graph because negative 1 is the vertical asymptote. And so we start having some properties about where these asymptotes occur. So when we look at rational functions, we got to be able to pull a lot of the attributes out just by looking at the equation. Some of the formal definitions, so a rational function is just that when you have a polynomial divided by a polynomial, so n of x and d of x are polynomials, and again our domain d of x, that polynomial, that equation cannot be 0. Vertical asymptote is the line x equals a, which is a vertical line, where as x approaches some a value, then the y values approach positive and negative infinity. And then a horizontal asymptote would be the equation y equals some number b, and then that's going to occur wherever y approaches b, x approaches positive and negative infinity. So I kind of mentioned that in the previous page. So given the function, the rational function, n of x over d of x, where they're made up of these polynomials, and this mess up here is just kind of a fancy way of saying polynomials. But the reason why I want to do that is because you've got to look at these terms. So look at the first term. This is the degree of the numerator, where a sub n is the leading coefficient, and n is the degree of that. And then on the denominator, we have b sub m is the leading coefficient, and m is the degree of that polynomial in the denominator. So we're going to use that notation down here below. So we have vertical asymptotes occur wherever we have zeros in the denominator. So that creates a vertical asymptote, like I mentioned in the previous problem. Horizontal asymptotes. These occur in 3 different scenarios. You always compare the degrees of n of x and d of x. So the degree of polynomial n of x is the n, and the degree of the d of x is m. So we're going to use that notation down here. So if the numerator's degree is smaller than the denominator's degree, if that's occurring in the rational function, then we automatically know that y equals 0 is a horizontal asymptote, which is the x-axis. If the degrees are equivalent, the same, then you need to divide the leading coefficient. So divide the leading coefficients. That's your horizontal asymptote. Y equals whatever that value is. If n is bigger than m, so that the numerator's degree is bigger than the denominator, there's no horizontal asymptotes. But there could be a slant asymptote. Could be. It doesn't always be, it could be. To know if it's a slant asymptote or oblique, which just means it's not horizontal vertical but it's another line, it occurs when the degree of n of x is 1 more than the degree of d of x. So whenever you have a numerator's degree is bigger by 1, to find that slant asymptote where it occurs, you long divide the two polynomials. So the equation of the asymptote is the quotient you arrive with without the remainder. So you don't use the remainder portion, but use the other part of the quotient. So it's really the slant asymptote. So holes occur at values where the function d of x is undefined, but there are no vertical asymptotes. So in Algebra 2, you really don't talk a whole lot about holes. This is kind of a new concept for rational functions. When you're looking at these rational functions, you look at here, let's see what we can pull out. We see how we have squared and squared, so we look at our horizontal asymptotes. Because the degrees are the same, we look at the leading coefficients, and it's going to be y equals 1 over 1 or 1. So that's why I know my horizontal asymptote is going to occur. And so our vertical asymptote, we have to find that by setting our denominator equal to 0. So we find the zeros of our denominator. And so we can factor this. Just going to be x plus 3 and x plus 1. And so it appears that we should have, so we could say that x cannot equal -3 or -1. So it appears that those would be the vertical asymptotes, -3 and -1. But they're not both vertical asymptotes. And the reason why is if we factor the numerator as well. The numerator was x plus 3 times x plus 1. And that was the denominator. The numerator, if we factor that, we get x plus 3 times x plus 3. So if you look at what happens here, because it's all multiplication, the x plus 3 is reduced here. Whenever that occurs, when you are factoring or reducing out a factor from the numerator and denominator, that creates a hole. So this process here is the hole. So I know there's going to be a hole at x equals -3, the 0 from that. So we want to figure out where the hole occurs at. What's the y value? You can plug in to the rest of the equation the actual x value. So our result was x plus 3 over x plus 1. If I plug in x equals -3, I find a y value of 0. So -3 plus 3 is 0. 0 divided by -2 would be 0. So the vertical asymptotes is still this -1 over here. So at x equals -1 is a vertical asymptote. So we also have a hole at the point -3, 0. Which means at that one point, there's no solution. It'll approach that point, but it won't actually be. And this is hard to find on the calculator because it looks like there actually is a value there, but it's not. If you use the table feature, you'll see it's an error, but on the calculator, on the graph, it looks like it goes through that. So if we were to graph this, I right away would draw these properties. So horizontal at 1, vertical at -1, and then a hole at -3, 0. So right here I draw open hole. So there's my start to my graph. Now I can then just plot points. So when I'm making my table to graph this, and let the calculator help me out, what I do is I do both sides of this vertical asymptote. So we have -1 here. So I always, -1 I know is going to be undefined. It's going to be an error. It can't do because it's a vertical asymptote. But I'm going to go on both sides. So I do -2, -3, which I know the answer, -4, and I can keep going. And a lot of times we have to do decimals as well. 0, 1, 2, 3, and I can plot other values like that to help me graph it. And these might not be enough to plot. I might not have enough here to see what's really going on. So at -4 we're at 1/3, -3 is undefined, -2 is -1. So I kind of see the shape here now. I know it's going to go through this hole. And then we have 0 is 3, 1 is 2, and then 2 is 1 2/3, 3 is 1 1/2. So you kind of see how it's approaching. And so I can kind of sketch the curve where I'm connecting the points, knowing that we're approaching the asymptotes. So we really got to use these asymptotes to our benefit to know that we're approaching it but never touching it. And so you see how the hole here, we leave it as an open circle so I know it can't be that value. And then we have the asymptotes, vertical and horizontal. So that'd be a quick sketch of that. So here's another one. So if we look at 3x squared plus 1 over x, looking at our horizontal asymptote, horizontal, it's none, because the numerator's degree is bigger than the denominator's. So I know it's none. The vertical is just going to be x cannot equal 0, because that's what we can't have in the denominator. And then we don't have any holes, so I could put none for holes because I can't do any reducing. There's no x to factor out on the top. But there's something else here. This one has a slant. It's a slant, I know, because the degree of the numerator is bigger by 1. So to figure out where the slant occurs, we have to long divide by the 3x squared plus 1 divided by x. When I do that, I need to include the 0x term here. So let's long divide. So x times 3x is going to be 3x squared. So now I multiply 3x times x, 3x squared, I subtract, I get 0, drop the next number, so drop the 0x, so we get plus 0x. We want to do plus 0 here, so we get 0x, drop the next number, plus 1. You can't divide that, so then 1 is actually the remainder. So 1 is the remainder, so we have 3x plus 0 plus 1 over x. That would actually be the answer if you're long dividing. What we want to find the slant asymptote is everything except for the remainder. We don't use the remainder, we use everything else. That portion is going to give us the slant asymptote. So it's going to be like y equals 3x plus 0, so it's in the slope-intercept form. So when I'm sketching this graph, I can then plot this slant asymptote 0 and go up 3, right 1 to find that shape, or down 3, left 1, and we get this shape. So here's a slant asymptote. We also have a vertical asymptote at x equals 0. So here's the vertical asymptote. So now we have the rational functions, those two branches or curves, are going to be on opposite sides of these kind of sections or pieces of the graph. So we still need to make a table for the function here for 3x squared plus 1 over x. So again, I'm going to make both sides of my 0 value. So I know 0 is error. So negative 1, negative 2, negative 3, and 1, 2, 3. So we can just use a calculator, or we can plug it in by hand. So it actually ends up being inside this. Negative 1 is negative 4, and so I'm not quite sure what's happening. I see the asymptotes here. It's kind of hard to see. 1 is 4, 2 is 6.5, 2 is 6.5, but I can see the sketch here. You're going to come in here and have a sketch of the two branches off of it. So but there's a slant asymptote. So to graph the functions, this kind of what I was doing. You need to state the domain. The domain a lot of times helps us find the vertical asymptote. You're going to simplify important because then you'll see your holes. So you can find and plot the y-intercept using f equals 0. So you're plugging 0 in for x and plotting that. And the ones we did, a lot of times we plotted those just on the table. You find and plot the zeros of the numerator, which are the x-intercepts. And that's kind of the rule that when fractions equal 0 when their numerator is 0. Find the zeros of the denominator and plot the vertical asymptotes and holes. Find and sketch any other asymptotes. Plot at least 1 point between and 1 point beyond the x-intercept and vertical asymptotes, and then complete the graph using smooth curves. And we really use the asymptotes to help us finish this, to complete the graph of the smooth curve. They approach the asymptotes. So that's it for 2.6 and 2.7 for the first day of it. We will go through this another day, but this is the video for both sections. We do have a video problem, so this is your video problem. When you do this, I want you to make sure you write out if there's a horizontal asymptote, what is it? If there's a vertical one, what is it? Well, if there's a slant, yes or no? If so, what is it? Are there any holes? So you need to go through this first. And to graph it again, we're going to make a table, look on both sides of the vertical asymptote, look for the x and y intercept, and then you're going to use your asymptotes to have your graph go towards the asymptotes. So there you go. Have a good night.